We've come to the final step in our hypothesis test, drawing our conclusion. To do this, we will compare our p-value to our alpha. If our p-value is less than or equal to our alpha value, we reject the null hypothesis. If our p-value is greater than our alpha value, we fail to reject our null hypothesis. In this case, our alpha value was 0.05 and our p-value was 0.423, so we fail to reject our null hypothesis. If the null hypothesis was true, we'd expect values this extreme about 42% of the time. That's fairly common, so I don't feel confident that the differences observed between the means of the samples is significant. Notice that our hypothesis test can only reject the null hypothesis or fail to reject the null hypothesis. We can never say, for example, the null hypothesis was proven correct. This is because it can never prove the null hypothesis true unless we test the entire population. The trick here is that it's easier to show a statement to be false than prove it true. For example, consider the statement, all flamingos are pink. To prove this, we need to examine all flamingos in the world. However, if we observe just one black flamingo, we can reject the statement, all flamingos are pink. Or, to use a quote attributed to Albert Einstein, no amount of experimentation can ever prove me right. A single experiment can prove me wrong. So, while our sample wasn't able to reject the null hypothesis, it also wasn't able to prove it. The only way we could prove it is by testing the entire population. The results of our test might feel disappointing. The actual difference between the means of our samples is quite large at almost 13%. Over a year, a difference of 13% could be a lot of money. But our test, using the sample size we had, wasn't sensitive enough, so we can't be confident this difference actually exists. What went wrong here? Earlier, we talked about how sample sizes over 30 are generally good enough, though samples of 100 are much better. We're working with a sample size of 750, so shouldn't that be pretty sensitive? Recall that in some situations, we may need much larger sample sizes. One such situation is when there is a low rate of positive cases. If you examine the observations in our data, only about 10% of visitors end up purchasing a vacuum. That means our samples are being determined by about 75 individuals, so there is a fairly low rate of positive cases. Not only that, but within those 75 or so individuals, there's a lot of variance, with some buying the vacuums for half off and some buying 2 or 3 vacuums at full price. Our average standard deviation is $174. A high variance and a low rate of positive cases can really hurt the sensitivity of our test. In hindsight, we probably should have looked at the historical conversion rate of our customers when determining our sample size, or looked at industry averages for an estimation of what to expect. If we had expected a high variance and low conversion rate, and we knew we wanted a sensitive test, we might have known to pull a larger sample. Even though we didn't reject the null hypothesis, the best practice is to still report these findings. For our next step, we should not pull a new sample of the same size and redo the test to see if we get a different result, or go back and remove outliers to try and make it significant, or change up the variables, like looking at only results from the US. Or if our result is close to our alpha but not quite small enough, we don't want to add 2 to 3 more observations to see if it changes. These are all examples of p-hacking, and these actions dramatically increase the chance of a false positive. Of course, we may want to try this experiment again with a more sensitive test. In Chapter 5, we'll explore how to do this properly by first doing a power analysis. You may have noticed in our spreadsheet that we captured a third sample labeled None. A fundamental premise to this entire experiment is that having a warranty, any warranty, will sell vacuums better than having no warranty. Do our visitors really care about warranties? Does it actually change their buying habits? Well, we have the data to test this. We'll perform another hypothesis test with a random sample of 750 visitors who were not offered a warranty. This sample is drawn over the same time period as our other two samples to limit any seasonal bias. For this t-test, our null hypothesis is again that there is no difference. But for our alternative hypothesis, things get a bit different. We could repeat what we did before and set our alternative hypothesis as simply there is a difference. But what we're actually interested in is something more specific. We want to know if showing a warranty is better than not showing one. So let's state that as our alternative hypothesis. For this test, we will focus our attention on the left side of our distribution. We'll leave our confidence level at 95%, meaning we'll reject the null hypothesis if our test shows a value less than the leftmost extreme 5%. Since we are only rejecting the null hypothesis if it falls to one side, we will use a one-tail test. Next, we'll repeat the same process as before. Let's duplicate our tab from before. We'll leave our first variable range as the full warranty group. That was our smaller mean of our warranty samples, so this is a conservative approach. You could also draw a new random sample of 750 from our two warranty samples, but leaving it as it is will make it easier to follow along and get the same results. Next, let's duplicate the tab. Right-click the tab. Move or copy. Move to the end. And finally, check Create a Copy. And let's name that tab 5-year versus none. Now, let's go back to our data. Filter for none. Copy our data, paste it in our new tab, rename our column, and then we can run our test. Again, you'll want to navigate to the Data tab, then Data Analysis, then select t-test to sample assuming equal variance. For our variable 2 range, we'll use our none values. The hypothesized mean difference remains 0, and our alpha remains at 0.05. And we'll post our results in this worksheet at the top. Click OK. This time, we'll want to select the first P that says one tail, and our value is 0.022. We also want to check that the mean for our second variable, the no warranty sample, is actually smaller, which it is. This tells us that our sample falls to the left side, as our alternative hypothesis predicted. Since our p-value is less than our alpha of 0.05, and the no warranty sample is the smaller value, we are going to reject the null hypothesis. We can be confident in our alternative hypothesis that the mean sales of customers shown a warranty is higher than the mean sales for customers not shown a warranty. That doesn't mean the difference is actually $16 or so. We're just quite sure there's some difference. The question we're exploring is whether there's a significant difference between divorced or married prospectives' response to a bank's marketing campaign. Specifically, is one group more likely to subscribe to a term deposit? Unlike our previous example, this is a simple, binary yes or no measurement. Our null hypothesis is that there is no difference between these groups. Our alternative hypothesis is that there is a difference. That alternative hypothesis tells us that we need to use a two-tailed test. To start, let's open a new sheet. We'll copy and move the data here so we don't have to mess with our original data. Let's create a filter. Select only the divorced people. Then copy that into a new tab. And remove everything but our conversion column, which we want to give a new header, so we remember which sample this is. And then repeat these steps, but for the married people. And keep only the data points that we like. Again, change the header so everything is clearly labeled. Let's go to the Data tab and open the data analysis. Now, which t-test should we run? Well, we'd use the pair test if we were showing each subject both variables, like having each subject do a blind taste test of Coke and Pepsi. In this case, each observation is a completely different person, so this isn't the right test. We'd assume equal variance unless we have a good reason to assume the variance might be different. And in this case, we do have a good reason. Because we actually have a lot more people in our married group than are in our divorced group. When the number of observations for each group aren't the same, we'll want to use the unequal variance test. And you'll notice that we get a warning that the input range contains non-numeric data. This is a bit of a data labeling issue. Excel isn't able to run this test on text strings, so we have to convert our text into numerical data. The number we pick is a bit arbitrary, but it makes sense to have a no equal a 0 and a yes equal a 1. For simplicity, let's just use the find and replace feature to change our no's to zeros and yeses to ones. Sometimes calculated if statements might be a better choice. It would be a bit more fail-proof if an error appeared in our data, but for this data, I know find and replace will work. So press Ctrl and F, then go to the Replace tab. Replace no with 0, and then yes with 1. Let's try our t-test again. Go to the Data tab, Data Analysis, and then select t-test, to sample assuming unequal variance. And our result is 0.000175, which is highly significant. Our difference, or the actual effect size, isn't that much in this test, but our certainty is quite large. This is thanks to a solid sample size and less variance in our samples than in our previous test. And real quick, to show you that the numbers we choose are somewhat arbitrary, let's replace all the zeros with 52. Run the test again, and we get the same p-value. But I do like the 0 and 1 method much better, as our mean is actually the same as our conversion rate for the campaign. Now, you could run this test a different way, perhaps grabbing a smaller sample. If you just selected the first 5,000 users in both samples, and then assumed equal variance, that could work. But be careful. In fact, when we do this, notice that our mean drops dramatically for our divorced group. So does our p-value. What's going on here? Well, we did cut off 207 observations from the end of our divorced group, but it's odd that small change in sample size would change our measure. Let's head back to our original dataset. Notice our samples are arranged by date. We might have unintentionally introduced a bias. By taking the first 5,000, we're cutting off the very last dates of our campaign, and looking at that period, it looks like conversion was quite high. Without even running the calculation, I can see quite a lot of conversions, easily over 10%. It's possible there is a seasonality effect, and September to November are particularly busy months. Springtime is usually a busier time for banks, and this is a Portuguese bank, but it would be springtime in Brazil. Perhaps a lot of their customers are Brazilian. It might also be partial due to time pressure. A marketing offer that's ending soon might drive conversion better. Let's check if our married sample sees the same spike. Yep, it does. If you're grabbing a smaller sample from a larger data set, a good practice is to just do a quick random sort of your data. Type equals rand and brackets, then double-click the corner. Do a sort. Then grab your data. This means we're not unintentionally sorting by another variable and introducing bias. An extra layer of random never hurts. One last note, with a data set like this, with multiple variables, a really good place to have started our analysis would actually be with an exploratory data analysis, or EDA. This would help us quickly identify variables that contain correlations. We won't be digging into how to conduct an EDA in this course, but you can check out our Data Science Fundamentals course for more on this topic.